I just I'll give it away. Maybe I read wrong. Still, I saw your name on. Maybe I don't. You would know better than me. I heard. This is the
Yeah, that's right. Yeah.
Yes, yes.
Let's begin. So, welcome everyone to the final day. Our first speaker for the morning is Shannon, and talks to us about giant gravitons on toilets as defect systems. So, thank you.
Thanks, Gary. Good morning. So this is the third part of my lectures. So in the previous two lectures, we reviewed some results, some old results with 9 years old, to give you an idea of how Bootstrap works in these holographic setups. And today we are going to use these to look at something more interesting. So the technical talk today is based on a paper from last year and some work that should appear shortly. Okay, so what we talked about in the past two lectures, the goal was to, in some sense, to try to harness the computational power of ADS-TFT. So in seeing these previous lectures, doing brute force calculations in ADS-TFT is actually quite hard, and in order to more get more out of this correspondence, we should be able to find a way to do these calculations more effectively. And the trick is to, instead of starting from Lagrangian and then follow the steps, shortcut is to impose symmetries and conditional conditions, and that's the idea of Bootstrap. So I explained in my last lecture, as I explained in my last lecture, this approach was first applied to the case of 4D and dispersive real mills. And there we were able to obtain all the holographic 4-point functions without computing Witten diagrams. And the strategy is not, the success in that particular model was not a coincidence. Actually, the strategy is very general and it has been applied to many different theories with varying amounts of supersymmetries and in different spatial dimensions. So in addition to like in 40 angles force mills, where we're scattering essentially gravitons in ADS, you can also scatter gluons in ADS, and then you can sort of try to see, to have an analog of the amplitude programming in flat space. And indeed, there are many nice parallels. So there have been a lot of developments in the past 10 years for these holographic collators. However, it's easy to see that there are still some obvious but important limitations. So one is that in the previous results, we only focused on operators which are light. And moreover, for example, in the 40 angles dispersive mills, we were always working in the planar limit. But there's also very interesting physics when it's non-planar. And still in this canonical example of ADS-TFT, it's not difficult to find situations where we encounter those issues. In this series, there's an interesting class of operators known as joint graviton operators. So they take the following determinant form. where I think maybe for this X in my lecture, so the phi's are the 6 scalars of n equals 4 supermills. And the T is the same null vector I used to capture the asymmetry polarization. So this operator has conformal dimension delta equals to n. N is the rank of the gauge group, so it's SUN. And the asymmetry limitation is 0 and 0, so it is also a half BPS operator. So the supergraviton operators we looked at in the previous lecture, they are due to gravitons. But these joint graviton operators, the interpretation is different. In the bulk, they are due to extended objects, which are these D3 brims. Now, because of this determinant form, the one-over-one counting is different. Using these determinant operators, we can actually access non-planar features of the theory. And these operators are also interesting targets from the perspective of integrability, because these determinants, they're more precisely, these are the maximal joint gravitons. They actually also preserve integrability. Okay, so what do we know about these joint graviton correlators so far? So it turns out that actually many things are still not known. Most studies in the literature, they focus on the case of 3-point functions. For example, you have 2 heavy these determinant operators and 1 light operator. But these 3-point functions, they are in a sense kind of trivial, because as we learned in previous lectures from, for example, Costis, you know that 3-point functions, the form of 3-point functions are fixed by conformal symmetry up to an overall number. So the interesting physics in 3-point functions is only contained in this number. So this is still a non-trivial number because it depends on coupling, but it does not have non-trivial kinematical dependence on where you insert your operators. The next non-trivial case is 4-point functions. So here we are considering where you have 2 giant graviton operators and 2 light supergraviton operators. And studies about these objects are usually only in the literature, they're only in the weak coupling limits. So people have computed these 4-point functions up to 3 loops in weak coupling. And strong coupling, there's almost nothing known about these objects, except there's some prediction from using localization techniques. So the localization can compute certain integrated correlator for a special case of these 4-point functions, where these 2 light operators are in the stress tensor multiples. So the light is the supergravitons. And what we want to do here is we want to systematically go beyond what is known in the literature. And we will do this by introducing some new techniques as well as new ideas. So the most important ingredient to make this for making this progress is to view disjoint graviton operators as defects. The defects are some extended objects in the theory. So you can add these to your theory to make the dynamics more dynamics richer and more interesting. And there's like applications of of defects in from different perspectives. So in experiments, like you have boundaries, impurities, these are defects, but also formally you have Western loops, D-brims. They are also can also be viewed as defects. So in the previous lecture, I told you how we can use bootstrap ideas to compute holographic correlators in defect-free CFDs. But these techniques can actually be quite straightforwardly extended to series where you have conformal defects. And this extension has been developed in a series of recent works. Okay, so right, so in this series of works, it's about like defects like with generic dimensions. Now, how do giant gravitons fit into the story of defects? Because it seems like they don't quite look like defects. To understand that, the question we need to figure out is what dimensions can defects take? So here I'm considering a defect with dimension p, and to understand what values p can take, it is useful to go to the so-called embedding space to understand how symmetry gets broken. So this embedding space actually already showed up in Tarek's lectures. So essentially what we need to do is to go to 2 dimensions higher. So let's say you have a d-dimensional CFT, you should go to d+2 dimensions. Then in this higher dimensional embedding space, the conformal symmetry gets linearized. So if you restrict yourself to only d dimensions, then, for example, special conformal transformation is a nonlinear transformation. But in d+2 dimensions, this is just a rotation. Okay, so the conformal group in d dimensions is SO d+1, 1, which rotates all these dimensions. So the red one is time-like, the other ones are space-like. Now, when you insert a defect, basically you're separating these dimensions into 2 groups. So the first group corresponds to the dimensions occupied by the defect. So this is still in the embedding space. So it's p+2 dimensions. And the rotation, keeping these rotating these directionally into each other, is the residual conformal group, which is SO p+1, 1. And in addition to that, you also have a transverse rotation that keeps this part invariant, but rotates the other group. And this is a SOD minus P factor. Now, the defect-free case can be viewed as P equals to D. So you have like sort of space-filling defect. And usually when we think about defects, we start from P equals to 1. So P equals to 1 is line defect. And you can also have a surface defect, which is P equals to 2. You can go all the way to D-1. So this is like a boundary or an interface. But from this embedding space perspective, actually, you can see that we can ask P to take more values. Essentially, just require, like in the first group, you have at least 1 dimension. So this allows you to enlarge the values, the range of P from this to -1 to D. So you get 2 extra new choices where P goes to 0, so it's 0-dimensional, and -1. Okay.
Flat defect.
I'm assuming a flat defect. Yes. Yeah. It's
P equals 0 is the point, but I can get to that. -1.
Yes, I'm going to explain the next slide. Yes. So these numbers, they seem a bit weird. Like, so how do we understand these exotic numbers? An easy way to help you understand these numbers is to use holography, right? Because the general lesson we learn from ADS-CFT is that when you consider the bulk dual, objects usually gain an extra dimension, right? Then it's easy to make sense of these 2 numbers. So P equals to -1. So what does that mean? -1 dimensional defect. That corresponds to a 0-dimensional point in ADS. And P equals to 0 will correspond to a line in ADS. And this is actually consistent with what the picture we have for these stranded gravitons, because as mentioned, these stranded gravitons are these 3 branes, which occupy S3 instead of S5. Now these guys are 4-dimensional, so S3 is 3-dimensional. You still have 1 dimension left. So that makes these giant gravitons to behave like some heavy semi-classical particle that goes along a geodesic line. So in this picture, these orange dots are where I am inserting the giant graviton operators, and the giant graviton travels along a 1-dimensional geodesic line in ADS.
The point is that they don't back out, right?
Yeah, so very good. So the giant gravitons, they have dimension n, so they're not heavy enough to back react to the geometry. Yeah. Here I'm not going to talk too much about the P-1 case. I'll just mention that it can also be realized in 4D n equals 4 Mills by putting the theory on a real projective space. So basically you need to do a Z2 quotient, and you can also realize these -1-dimensional defects. Okay, so for P equals to 0, at this point, it seems a bit of self-evident, right? It's like a very natural idea, like in the bulk, you have a line. So it turns out we can actually get a lot out of this seemingly some trivial idea. And the point I want to make here is that we can actually turn this intuitive defect picture into a concrete computational framework. And this defect picture also allows us to see some hidden structures as I will discuss in more detail. Another comment about these P equals to 0 defects is that they are in some sense more interesting than defects of other dimensions, because here these correlation functions, right? So you have 2 giant gravitons and 2 light gravitons. These 4-point function can be they can be also interpreted as a defect for a 2-point function. So you have 2 dual interpretations. One is a defect-free 4-point function of local operators. The other one is a 2-point function in the presence of defect. Yes. So here is the plan for the rest of the talk. So first, I'm going to explain more precisely what this defect picture means and how we can make use of it as a computational framework. Then I'm going to show you by extending the techniques we saw in yesterday, how we can bootstrap all infinite many 4-point functions with giant gravitons and light gravitons in the limit where the Tohoe coupling is infinite. And the result will allow us to uncover an interesting hidden structure at strong coupling. And quite interestingly, this hidden structure that we observe at strong coupling also turns out to exist at weak coupling. And
There are 2 operators in the bar and there's a defect. Yes, not on the defect.
Not on the defect. Yeah. Right. So just so that we're on the same page, let me state that again. So we have 2 types of operators. We have the giant gravitons. These are determinants. And then we have the light supergravitons we talked about yesterday. These are the traces. But both operators, they are LPPS. And this is the important point. And the observable, we are interested in computing these 4-point functions where you have 2 of these light operators inverted at 1 and 2, and 2 heavy operators inverted at 3 and 4. Okay. Now, again, as in yesterday, because we want to do the bootstrap, so we need to understand the implications of symmetry. And as I mentioned, you have 2 interpretations, right? You can view them as 4-point functions in a defect with CFT and as defect 2-point functions. So we can try to understand this from 2 complementary perspectives. So let's first do the easiest thing. Let's first view them as 4-point functions. And this we already reviewed yesterday, right? So superconformal symmetry tells you that you can write the 4-point function as the sum of the free part and a reduced part. And the reduced part is multiplied by some factor determined by superconformal symmetry. And here, just to remind you, like these are the cross ratios we defined yesterday. Now, we can also view them as 2-point functions. So how are we going to do that? So a natural prescription is to divide the 4-point function by the 2-point function of the heavy operators. The motivation for that is if you want to think of it as a defect correlation function, you do not actually see the quantum numbers of the defect. So to get rid of these quantum numbers, you just divide by the 2-point function, right? So this inhomogeneous scaling, will get canceled out. But still, there's information about, where you invert these operators and their polarizations. So let's try to understand this a bit better. So usually when we talk about defects, we will say like the defect is aligned with x1 direction or and x2 direction, right? That's how we describe them, like in which direction they are aligned. But there's an equivalent and equivalent but more convenient language to describe these defects using projectors. So to define them, we again go to the embedding space. So this is so the x is the coordinates of RD, and we add 2 more dimensions to make it embedding space vector. And P, you can check for yourself, it is actually a null vector, okay? Now we have the P's for 3 and 4, and out of them, we can construct such a thing, which I call NAB. And this rank 2 tensor, you can easily check. It is a projector because n dot n will again give you n. And the geometric meaning of this n is to project in embedding space to the plane spanned by P3 and P4. Similarly, you can also do it for the asymmetry part. So let me remind you that T is also null vector, right? So T squared equal to 0, just as this piece. And you can also define a thing called a MIJ as a projector in the asymmetry space. There's a small difference, which seems a bit of unclear at this stage, but I will show you it's going to be very natural later on. So the small difference is like instead of writing it like that, we do 1 minus that. And the geometric interpretation is that instead of projecting to the plane spanned by T3 and T4, we are now in the orthogonal space. Now, using these projectors, it's straightforward to write down correlation functions. So the 1-point function, just like 3-point functions in defect-free CFTs, is completely determined by symmetry. So the only thing you can write down using embedding space vectors and these projectors is the following object. That's the only thing you can write down. Up to some overall coefficient AK, which is not fixed by symmetry. And you can write it out using these definitions. It takes this form. And then you quickly realize there's nothing but the ratio of the 3-point function ODD divided by the DD 2-point function. And this agrees with this prescription here to define the defect correlate.
So these schematical aspects, they don't depend at all on the superators area. In general, in any CFT, if I have a 4-point function,
yes,
I can reinterpret it as a 2-point function in the presence of a 0-dimensional defect.
Yes, exactly. That's a very good point. But so far, it doesn't care about this heavy or light. But toward the end, I will show you that this picture of defect makes sense. Actually, you're sort of required to think in that way when the 2 operators are heavy. So far, we're not seeing that. Yeah.
And there's no notion of maximality.
Sorry, say again?
There are notion of maximality at this point. Are we imposing that it's?
So far, no.
No.
But yeah, I mean, kinematically, they are the same. But later on, I'm going to focus on maximal joint gravity.
It's not, doesn't depend on this projection.
Yeah, so far it doesn't matter. Yeah. Okay, now when we go to 2-point functions, symmetry is no longer powerful enough to fix everything. So out of these sort of building blocks, you can construct cross ratios. So for the conformal part, you can construct these cross ratios, Xi and chi. And these can be related to the UV cross ratios we defined for 4-point functions. Okay, now what about supersymmetry? What does that imply for the defect 2-point function? We already know the answer because we know what that implies for the 4-point function. To get 2-point function, we just need to divide the 4-point function by the DD 2-point function. And our previous result for 4-point function now becomes this form. Okay, so you have a free part, and then you have some factor multiplying some reduced correlator. So here I will point out a technical detail, which actually will be important for us later on, is that in this reduced defect 2-point function, the quantum numbers are shifted. So the conformal dimensions will be shifted upwards by 2, and the asymmetry charges will be shifted downwards by 2. In particular, if you consider the lowest KK modes, where K equals to 2, this reduced correlator actually does not carry any asymmetry. It's an asymmetry singlet. Okay, so that's everything we can say from just the symmetry. Now to do the bootstrap, again, we also need a bit of dynamic input, just a little bit. So for this purpose, it's useful to briefly review what giant gravitons look like in the supergravity. Yes.
Yeah, sorry, maybe I missed this. Where's that 2 come from?
The weather
In the
what?
previous slide,
Yes.
the shift?
The shift?
Where
It's
does, yeah, where does
Yeah,
it-
it's because in this factor it carries quantum number, it carries weight.
2.
Yes, so this carries conformal dimension -2,
Okay.
and R charge 2. They're shifted in different ways. Yeah. Thanks for the question. Now, how do we describe giant gravitons using supergravity? So this is essentially captured by the action of D3 brane. So you have a dBi plus Wilsonino. And here, let me write the coordinate metric in a way that is convenient. So what I'm doing essentially is I'm basically putting the geodesic line to be at the center of the conformal boundary, and it goes upwards, like perpendicular to infinity. And the line is parameterized by this parameter tau here. And in the other directions parallel to the boundary, these are these xi's. And similarly for S5, these YAs, they are the coordinates for S3. And then you also have 2 transverse directions, Q and phi. Now, the maximal giant graviton solution is Q equals to 1 and phi equals to I tau. This is the classical solution. Then on top of that, we can consider fluctuations, and that correspond to localized fields living on this line defect in ADS. The next thing to do is to integrate over the internal S3 to get a one-dimensional Lagrangian in ADS. More precisely, not only we need to integrate over S3, we also need to integrate over the moduli of the solution, because I can get a new solution from the previous slide by shifting tau and phi. So in order to get the right answer, you also need to do this sort of orbit averaging. And once you do that, and then you expand in the fluctuations, you are going to get the following effective action in this form, right? So here, these different terms, M and N, correspond to how many fields you have. So M labels the number of defect fields, and n is number of bulk fields. And for example, this term 2, 0 is the connected term for the fluctuations on the defect. So from that, you can read up the spectrum. And this 0, 1 is useful as just to have one bulk field. It's useful for computing one point function. And then you also have more of these guys. So in the end, we are not going to use any explicit form, any explicit details of these vertices. We just need to know some rough features. And here I want to point out some rough features which are sort of special to this 1D defect in ADS. They're not shared by higher D, so they are sort of more interesting. So the first thing is this 0, 1 vertex. So that tells you how the defect is coupled to just one, how it's coupled to the bulk field, right? And the nice feature you see here is that that's not only coupled to the scalar bulk fields, but also to the spinning ones. And the coupling with this is a vector, these two are vector fields, this is the spin 2 field, and you can see it couples in the way of a minimal coupling. And this is also what we have, this is also what we expect for a particle in the presence of background fields. And also for these 1, 1 type of vertices, the interesting thing to notice is that now there can be an odd number of derivatives. This is because the line is 1D, and you can just take one. You don't need to construct the derivatives in order to preserve rotation invariance. And in principle, we also need this 0, 2, these sort of contact vertices, but they have some subtleties which are not resolved. But fortunately, we won't need that information at all because we can just get them from the bootstrap. Okay, so now suppose we know all the vertices, then we can just get the correlators by writing down all the Witten diagrams and then start the map. And there are 3 types of Witten diagrams, which I call bulk channel exchange, because there's a field getting exchanged in the bulk channel, right? Then there's also a defect channel exchange where you exchange a field that lives on a defect, and then there are these contact Witten diagrams. But to really follow this recipe, it's actually quite a nightmare. It's like a lot of crazy calculations you need to go through in order to do that. So we are not going to do that. We are going to do exactly what we did yesterday.
The actual diagram, the defect starts at minus infinity, right? Is that where it's
0.
It's just time that you are.
Sorry?
The embedding of the defect is in the time direction only, right? On the ADS side.
So here I have a wick rotated into Euclidean.
Okay.
So there's no time.
But it inserts at minus infinity and plus.
Actually, so you
Or
can
choose.
it doesn't really matter because you can do a conformal transformation to move these 2 endpoints. But convenient choice is to put this at 0, this at infinity. Yeah. Okay, so we want to do the bootstrap, and the algorithm is actually exactly the same as how we did it yesterday. More precisely, the potential space method, if you remember. So the idea is to start with an onstat, like you pick 2, KK levels, K1 and K2, and then you write an onstat in terms of all the possible diagrams that can appear. Bulk exchange, defect exchange, and contact. Just as in yesterday, these diagrams, the exchange part, they have the same form. So you have a Witten diagram part, and you also have an internal R-symmetry polynomial part capturing the exchange of R-symmetry corner numbers in the internal space. As I related to the comment I made earlier, so an interesting feature here is that these defect exchange Witten diagrams, they can now have 0, 1, or 2 derivatives. And for the contact part, we are just going to use the most general onstats with all the possible asymmetry structures, but we don't include any derivatives in the contact vertices. The reason is that we don't want the contact interaction to dominate in the high energy limit. Okay, that's what we expect from flat space. Okay, good. Now, another thing similar to yesterday is that you can also use these tricks to compute exchange weighting diagrams, and they also can be written as finite sums of these contact weighting diagrams. And these contact weighting diagrams, they are very simple, and they can be expressed as these 2f1 functions. Now, the last step is to impose superconformal symmetry. So that we also reviewed yesterday, to satisfy superconformal order identities. And if you implement that, you find all the coefficients you have assumed in the previous slide gets fixed uniquely. So this, for example, for the lowest correlator, where k1 equals to k2 equals to 2, namely strict tensor, you get a very simple answer for the defect 2-point function. The free part takes the following form, and the reduced part is actually simpler than the 4-point function we computed yesterday. Now it only involves weight 1, so just logs. Yeah. And similarly, you can go to higher values of k1, k2, and you can get an answer for all of these k1, k2. And we checked these results against some other things available in the literature. So, for example, even though we are computing things in the supergravity limit, this partial nonlinear normalization theorem allows us to get the free part as well. And this free part has also been computed in field theory. Basically, you just do some fancier version of wave constructions, and you find the free correlators, they agree perfectly. Now, in doing this bootstrap calculation, actually, I did not use any of these 1-point vertices. I didn't use any of these as my input. However, you can just do this. You can explicitly compute the effective Lagrangian and get their coefficients and compute the 1-point functions. And so that's an independent calculation, and you find it agrees with the 1-point functions, which you can extract from the 2-point functions. That's another strong check. And finally, I mentioned this integrated correlators for this 2-point function. So they computed for arbitrary coupling, then you can go to the strong coupling limit, and then you do the or integrate this 2-point function, and you find again the answer is in perfect agreement. Okay, so this is what we get from the bootstrap, but turns out very interestingly, the answer contains a quite remarkable hidden structure. And this is actually similar to a structure people observed for the 4-point function of light supergravitons. So I'm going to quickly review the 4-point function story in the next slide, but let me just say in one sentence what this means. So basically, the observation of this hidden symmetry for 4-point function was that you can package all these 4-point functions that we computed yesterday from the bootstrap into a single generating function. So the way to obtain this generating function is to start with the simplest 4-point function, 2, 2, 2, 2. And then, as I mentioned earlier, this lowest reduced correlator actually is an asymmetry singlet. It only depends on xij squared. So the trick to get a generating function is to replace the 4-dimensional distances on the boundary of the ADS by the 10-dimensional distances. So essentially, you need to replace xij squared by xij squared minus 2tij. And the meaning of this is just the distance in 10D. More precisely, you can put together the embedding space vector, which is 6-dimensional, with the 6-dimensional null vector for asymmetry, so that you get 12-dimensional. And then you replace this xij squared, which is essentially p1.p2 by z1.z2. And this 12 is 10 plus 2, right? So it tells you, it suggests you like this is the conformal invariant distance in 10 dimensions. So that was the observation of Karen, Hott, and Chin, and they managed to unify all these 4-point functions from Bootstrap. And to get them, you just need to tailor expand this generating function and collect all the terms that can appear, all the structures of TI. Okay, so that was the story for 4-point functions. What about giant gravitons? So if you try to do the exact same manipulation here for the giant graviton 4-point function, you find the prescription does not work. The reason is that when you do this expansion, you will inevitably also change the dimension of these giant graviton operators. However, we know that they should have fixed the conformal dimension and n, so you should not be changing that. So, but if you think a bit harder and use this intuition of defects, actually you can find a different realization of this hidden conformal symmetry. So let me explain how this works. So the thing we need to do is that we need to, instead of using the same replacement rule, where you replace pi.pj by vi.zj, you need a different set of rules for points 3 and 4, which correspond to the giant graviton defects. So the correct thing to do is not to promote these vectors, z3 and z4 individually, but you only promote the projectors formed by them. So what I mean by that is like for 1 and 2, you do the same thing. But there, in addition to P1.P2, there are also structures which you can write down. You can have PA dot the projector N dot PB, where A and B take values 1 or 2. You replace this guy by Z dot N plus M dot Z, where I remind you this M is the internal space projector. So let me first state this is a prescription, and you apply this prescription to the simplest correlation function, where k equals to 2. And then you find you get a generating function, which after Taylor expansion gives you all the other higher kk defect 2-point functions you get from Bootstrap.
Saying that less times growth melody.
Very good. I'll get to that in the next slide. Indeed, you will see there's some sort of break-in here. Other questions? Okay, so as Lorenzo pointed out, what we are going to get is some defect version of this hidden conformal symmetry. So let me first tell you intuitive but imprecise picture of this to understand this hidden conformal symmetry. So roughly speaking, what was happening for the lighter 4-point functions was that you can do a Weil transform because ADS phi times S phi, both factors, they have the same radius. It's conformally flat. So you can do a Weil transform to R10. That's why we are seeing these 12-dimensional embedding vectors. Then all these correlation functions, they basically just get mapped to a single scattering or single correlatory 10D. Now, when we have giant gravitons, I mentioned earlier that they are really 4-dimensional objects. They are D3 branes with 1 dimension in ADS, another 3 being S3 in the internal space. So they occupy R times S3. But this R times S3 is also conformally flat because it's just embedded in a conformally flat background. So after Weil transformation, this ADS phi times S phi becomes R10, and R times S3 becomes now 4. So you have a 4-dimensional defect in flat 10D. And this R4 is the D3 brane. And now it's actually very easy to understand why I define M with 1 minus. So you can look at this picture. So this 4D space has one component R. That's from the projector N. And then it should also have a 3 other dimensions from this S3. So this S3 is essentially the orthogonal part with respect to the 2D plane formed by T3 and T4, right? So I mean, total, yeah, I mean, right. It's orthogonal to that. That gives you the S3. That's why we want to define it with a 1 minus, so that projects the orthogonal space. And here, this total space, this 4-dimensional space, is obtained by the sum of these two projectors, M and M. And the picture now here is like all these defective point functions after Y transform gets mapped to sort of a scattering form factor of 2 light particles with a extended brim. And okay, thank you.
You have done the orbit averaging and stuff, right? So I thought you were not seeing the S3 very much. That expanding some factors.
Oh, we still do.
Oh, you still see that?
Yeah, you still. I mean, even after orbit averaging, it's still 4-dimensional. Yeah. Here, let me just very quickly mention there's a different way to see this hidden symmetry. So yesterday we talked about this mailing space as a momentum space for ADS. And here you can also extend it to include defects. The extension takes the following form. So basically, you consider the dual variables of these defect cross ratios, and these delta and gamma. They're sort of the defect, the one-to-one scattering Mandelstam variables. Now, to manifest this 10D symmetry, instead of just doing the Mailling transform for the conformal part, you also do it for the internal part. So in a sense, you are defining some 10-dimensional Mailling space. And the statement of hidden symmetry in this language is that regardless of your K1 and K2, the Mailling amplitude is the same and takes this very simple form. Okay, so now let me mention something quite interesting. So I just talked about this hidden conformal symmetry at a strong coupling, but we actually can also find it in the weak coupling limit. So in the case of 4-point functions of light operators, actually this was pointed out already by Karen Hott and Coronado. So there, a weak coupling, you can compute loop corrections using the method called Lagrangian insertion. And that defines you, so basically give you like these loop corrections as integrals. And so what they found is that their prescription at strong coupling applies to the integrands in this Lagrangian insertion method. Now for the giant gravitons, we find a similar story. You can also compute the loop corrections using Lagrangian insertion. For example, like at one loop, the integrand takes this simple form. And in general, at Lth loop, what you have is a L+2 point defect correlating, where you have these new insertion points at phi 6 and so on, all the way to L+4. Now, how does this prescription work at weak coupling? So you also define a 12-dimensional vector for these insertion points, except that the internal part you make it to 0. And then you extend the previous replacement rules by basically allowing A and B to be not just 1 and 2, but all the points except 3 and 4 will insert the giant gravitons. So using this very simple prescription, you find that the integrand of the lowest correlator, namely 2, becomes this boldface I, which is which is the generating function for these integrands. Then you just Taylor expand, and you can get this I K1, K2 at one loop for any K1 and K2. And so this is one loop story, and we checked also it works for two loops. So we think this is the true for should be true for arbitrary loops. Now, to address the question asked by Lorenzo at the beginning of the talk, here I want to say a little bit about heavy light correlators. So far, the discussion relied very much on supersymmetry, but there are some general lessons which applies to the case without any supersymmetry. So the observation is as follows. So let's look at some defect-free 4-point function, where the two light operators, they have some finite dimension delta 1, delta 2, and there are two other operators with large dimension lambda, and the lambda, we want to take that to infinity. Now let's look at the conformal blocks. So if you look at the S-channel conformal blocks, so that's the light, heavy channel, you find after taking lambda to be large, this conformal block of 4-point function just reduced to the bulk channel conformal block where the exchange operator in the bulk. More interestingly, for the T and U channel, what happens is that you should take the union of T and U channels after you take the large lambda limit. Also, like in this exchange, the operator should have dimension delta hat plus the large dimension lambda. So if you take this limit, you find T and U channel conformal blocks. They combine into the defect channel conformal block where the exchange dimension is delta hat. So the picture is essentially you have some sort of heavy background and you have fluctuation above that background. So once you subtract the background, you get the defect channel conformal block. So this is the purely kinematic statement because it just involves conformal blocks and tells you that whenever you're looking at heavy light operators, the most natural language the way to think about them is to describe them as defects. Yeah.
Does that calculation on taking random sublimity specifically, does that allow some simplification? There's also sort of operators that go like n squared.
So here I'm taking that strictly infinite, and then indeed there's some simplification. Yeah. But if like your operator is heavy enough, you can use it as a good approximation. Yeah. Right. Now let me wrap it up. So here I talk about maximal joint gravitons, but there are also other interesting things to consider using the same technology, such as the non-maximal joint gravitons, which are subdeterminants, and also dual joint gravitons. So these are not wrapped on S3, but they are in ADS. Also, there's a lot of data you can extract from these general results, and it'd be interesting to reproduce them from interoperability or localization. And here we consider one defect, right? Two joint graviton operators, but it's also interesting to look at multiple defects. The simplest thing to do is to look at 4-point function of 4 joint gravitons. So that is going to tell you about the interaction of two geodesic lines in ADS. And also there are already like systematic techniques in the literature allows you to use to go from the tree level supergravity to loop corrections as well as string corrections. And it's also interesting to consider more operators where it will probably reveal some analog locus properties with scattering amplitude in class space. And there are also many other different theories we haven't considered in this talk, but I think it's also similarly doable. So let me stop here and thank you very much.
Any more questions for our speaker?
So this action that you had in inside ADS, so you derived it from the water volume action of the liquid brain, right?
Yes.
But is there some sense in which this some universal action that would actually have a massive particle? would you just say, okay, I have a massive particle in seat, 5, let's say, just make this 5. It's very massive, but it couples in some way because I'm sort of seeing it. Does it fix the reaction or how it disappears the brain and so on?
I think you can, let's see. I think for the lowest correlator, like 2, I think it's a also sort of like condensed truncation. You can forget about the internal S3. So in that case, it is exactly just like a heavy particle in ADS5.
Okay.
Yeah.
But then if you consider also the ones that say that it's one position.
Right. Yeah.
Jay?
Yeah, maybe I can follow up on that particular question. So when you integrate out the S3 dependence, you get a point particle in ADS, right? How do you think about the dual giant but applying this to dual giant gravitons, because those are no longer point particle in ADS?
That's an excellent question. So at the moment, we don't know how to think about that. I think even the Witten diagrams are going to be a bit different because I mean, usually you do kick reduction only for the compact part. Now the non-compact thing is in ADS, so I think probably one needs to revise this strategy a bit.
About the rates for that computation, giving the wrong answer for some subset of that. Could you maybe expand a little bit on what the problem is there?
So okay, so let me just say, so yeah, it's some the subtlety is as follows. So if you naively just do this expansion and you get these contact vertices, and then you compute the Witten diagrams, and it's actually not specific to this case. It's like for any holograph defects, like you have sort of probe n in ADS. And so if you try to do an honest calculation, you find that the 2-point function does not satisfy superconformal symmetry. So the problem is not quite resolved, but I think we now get something that we are sort of trying to, maybe we are understanding it. The basic thing is like, the thing is like essentially, so you know, like in bulk, you need to sort of diagonalize the equation of motion in order to get the eigenstates. But that will receive some sort of correction on the volume of the program. And that the guess is that should be able to fix that, but we still need to see. Yeah.
Those kind of backgrounds?
Yeah, that's an excellent question. So far, I mean, what are we doing here is indeed it's been limited. Like we are not considering like back reaction and so on. But I think the general sort of like the philosophy should be also applicable, because I mean, if you want to compute things directly, that's going to be hard. But if you try to use symmetry under these conditions, even if you don't fix everything, it's still going to save you like a lot of effort. Yeah.
Final questions? If not, let's thank you again. I should be back at 11 o'clock. Next.
Pointer?
Just keep liking that.
No, it's okay. I was wondering if I see. Okay. Hi, everybody. Almost done. But before I get started, I want to say thank you for getting us all together. This has been great. I want to particularly thank the organizers. You guys all know who you are. Maybe we can give them a round of applause. Yeah, this has been great. It's my first time in South Africa. I hope to come back. Okay, so building on my previous lectures, I'm gonna tell you about a particular model, which is a very famous model in the history of quantum field theory, that we can use to learn a little bit more about physics in de Sitter, and particularly QFT in de Sitter, that is beyond the reach of other QFTs. Now, I'll explain a little bit more what I mean by that, but I'll spend a couple of slides talking about reviewing what I said in the previous two lectures about why basic notions of QFT on de Sitter are complicated or difficult. And I'm going to phrase it maybe in slightly different language than I used earlier, but it's okay. We'll see how it can. Okay, so here's a reminder of the geometry of de Sitter space. Remember, I called it the pseudosphere. It's exactly equation of constraint in d+1 dimensions, and because of this minus sign, as time goes forward, the spatial slices grow. And here are a pair of coordinates. You can clearly see that this space-time is time-dependent. Nevertheless, it's maximally symmetric, so it's a nice model of cosmology. It's a maximally symmetric cosmology. However, when we put QFTs on this space-time, like I told you before, there are things that we take for granted in flat space that we can't take for granted anymore on this time-dependent space-time. And we have to confront them head on. So let's talk about that. The first and most important lesson is that the Wilsonian paradigm doesn't work. Why is that? Well, let's look at a simple diagram that I could write down for any QFT. I have a massive particle of mass m0, and I let it decay into two particles of mass m1 and m2. And in flat space, such a diagram would be forbidden if m0, the rest mass of the original particle, was less than the rest masses of the two particles that came out. And the reason that that can't happen in flat space is conservation of energy. Very clear. There's not a kinematic space for momentum to be carried off if these masses don't have the right attributes or sizes. Okay. However, in de Sitter, you can have such a process where a particle of mass m0 decays into two heavier particles, because energy in de Sitter is not conserved. The space-time is time-dependent. There's no translation symmetry. And so this is no longer forbidden in de Sitter. And why did I say that the Wilsonian picture doesn't work in de Sitter? Well, if you take this to its logical conclusion, that means that the UV never fully decouples. If I wait long enough, I might have integrated out some massive physics above some scale, but if I wait long enough, then all of a sudden I can populate those heavy states and new physics becomes important. Let me give you a little bit more of a, so that was a very heuristic argument. Let me give you a little bit more of a clean argument for why that's true in de Sitter. Amplitudes, we can't really define amplitudes in de Sitter because unlike in flat space, we don't have asymptotic regions where we can define free Hilbert spaces. So the way that we make the argument in de Sitter is we go back to something called the Challen-Lehmann decomposition. So the Challen-Lehmann decomposition says that any interacting two-point function of a theory can be decomposed as a free two-point function, as a function of a mass squared times a density. And you may have seen a drawing like this in Peskin and Schroeder. The density usually has this kind of structure. There are some poles that describe particle states, and then there's a continuum that describes bound states of particles. Okay, well, the fact that there is a cut that starts at 2m0 squared is exactly the reason why this amplitude is forbidden from class 2. This cut and the zero of this amplitude are related. In de Sitter, like I reviewed last time, instead of working with m squared, we like to work with this thing called delta. And delta for a massive particle has this form where there's a complex part, nu. And the Challen-Lehmann decomposition in de Sitter, you write it like this. The integral over nu now times a free two-point function. And instead of having a cut, this row of nu has support on the entire real line. And because there's no cut, that means that this amplitude can be non-zero. That's the argument. So that was lesson 1. We don't have a good Wilsonian paradigm. Something that we take very much for granted. Lesson number 2 is actually perturbation theory in de Sitter is not very trustworthy.
Very small.
In some models, you can calculate them. I can give you papers if you want. They're very small. They're very small. If you don't wait very long times, you won't see it. Of course, it depends on your cosmological constant. If your cosmological constant is big, then the amplitude can be big. Okay, the second lesson that I want to tell you is that perturbation theory in de Sitter is not trustworthy at late times. Why am I concerned with late times? Well, remember I told you that de Sitter is an important geometry for inflation. And in inflation, we're looking at the last moment of the expansion of the universe, and we're looking at correlations across the sky. So this is the kind of diagram I'm talking about. This is the inflating universe, and we're looking at correlations across the sky. And usually they're computed using some diagrammatic techniques that look like this. We integrate over some interaction vertices in the bulk of this inflating universe. And there's a theorem that said that, and this theorem is due to Weinberg from 2006. And this theorem states that any diagram with n such vertices like this has a behavior at late times that goes like log of eta to the n. So eta is the conformal time to the n. So these diagrams have a logarithmic contribution at late times that is multiplied to the power n. And logs grow at late times. So this is a problem. So this tells us that if we try to use perturbation theory and also take a late time limit, those two limits don't commute. So we need to figure out a way to deal with these. And we actually don't know a very good way in general of how to deal with this problem. So perturbative physics is out the window. The next lesson is the one that I talked about yesterday. Massless fields lead to a violation of de Sitter invariance. I gave this example before. If you have a massless particle on de Sitter, you may think that this is a very reasonable Lagrangian. However, the two-point function is inconsistent for such a massless particle if you try to analytically continue it from the sphere. And actually, this tells you that the state for a massless scalar field is not de Sitter invariant. Or so there is something that we have to deal with, maybe some non-locality that we have to introduce in order to fix this problem. Yeah, so can we build good theories with massless particles? The last thing, the last lesson is that, okay, maybe we can take some integrable model on de Sitter and study de Sitter that way. And the last thing I mentioned in my lecture yesterday is that the ground state of de Sitter is thermal, because of this fact that in the Euclidean picture, the correlation functions are periodic in Euclidean time. And that makes integrability seem impossible. Let me tell you why. So often integrability is phrased in terms of some kind of a Yang-Baxter equation. So that means that that your interactions produce no particles. So if you have two particles coming in, you have two particles coming out. And the Yang-Baxter equation then says that a diagram that looks like this with three particles coming in should equal to the process where these two particles meet first versus where these two particles meet first. And that puts non-trivial constraints on the S matrix of the theory, and it lets you solve some S matrices cases. But this presumes no particle production. But I mentioned in de Sitter, the ground state is thermal. So there's thermal occupation even in a free theory. So this the fact that you can assume no particle production is already out the window when the ground state of a free theory is thermal. So here's the question: is there a suitable notion of integrability that can be applied to this? We don't know. So we have many questions, and we would like to address them slowly but surely. So we need a model. We need a toy model that we can use to address these problems. And I'm going to demand a few things from my toy model. One, my toy model shouldn't be a CFT. If it's a CFT, then it doesn't care about the geometry of de Sitter because de Sitter is conformally flat. So it would feel like de Sitter is the same as flat space. So it wouldn't be sensitive to the physics of this. Also, I don't want it to be free. I care about interactions. I want to understand how perturbation theory works. It should have massless particles. Massless particles, remember I told you massless scalars are weird. We don't understand them. So maybe if we can find a theory that has massless particles, we can learn something. And of course, we want it to be unitary.
It's supposed to be a model of your It's supposed to be a holographic.
I just want a QFT that has these properties. And I'm going to put it on this. Okay, so what model am I going to study? Well, here it is. Well, not the second. I should have. The model is the Schwinger model, which, yes.
Are your fields going to backreact with the geometry or not?
No, the geometry is going to be fixed. So the model I'm going to study is a model that was proposed by Schwinger in 1962. And it's a very simple model. It's the model of a Dirac fermion in 1+1 dimensions coupled to electromagnetism. So you have a charged Dirac fermion coupled to electromagnetism. The number Q is going to be my coupling strength for the E&M field. It's the gauge coupling. And the number P is I'm going to take to be an integer. This integer can be 1, 2, 3, 4. So this is a slight deformation of the original Schwinger model. In the original paper from 1962, P was 1. But I'm going to choose P to be any integer. Okay? And we call that number the charge of the fermion. Okay, so what does this model have? Well, it's a gauge theory, so it's gauge invariant. Under a transformation like this, and a shift of the gauge field like this, the action remains invariant. And there's also a chiral symmetry that the action has. So if I rotate my left fermion and my right fermion differently, then the action also remains unchanged. However, the chiral symmetry is anomalous. It suffers from the famous ABJ anomalous. Actually, the fact that the chiral symmetry is anomalous helps us to solve this model. So instead of doing a global chiral rotation, I can do a local one. And if I also subsequently shift the measure of the path integral, then this is how my action changes. So you see that there's a shift by the chiral rotation parameter here that competes with A. And this part also comes from the rotation of the path, as well as this piece right here. And this beta lets us solve this model because it gives us a frame in which we can cancel out the gauge field interaction. this is actually the secret that lets this model be solved. You can do a local chiral rotation, and then all of a sudden it lets you cancel out the interaction. And there's a way of keeping track of everything. So in some new rotated frame, the theory looks free, but actually the original frame. I want to mention one extra thing, which is the reason why we included this charge P, is that for P an integer other than 1, actually the chiral symmetry isn't completely broken. Actually, for P an integer, you can rotate by a discrete shift from n is 0 to 2p minus 1. And that is a non-anomalous part of the chiral symmetry. So for p not equal to 1, this chiral symmetry, which was continuous but anomalous, gets broken down to a discrete symmetry.
Sorry, beta is a number. How can you be used?
So what I mentioned was beta, this is the global chiral rotation. Instead, here I do a local chiral rotation. And if I do a local chiral rotation, then this is the way the action shifts. So if beta were just a number, this piece would be 0, this piece would be 0. But I still get this from the anomaly. And this is actually the anomaly piece. But for beta, any one of these numbers, this anomaly shifts the path integral by a phase, that is 2 pi I, because of flux quantization. So sorry, one thing I want to mention is I'm studying this model on the sphere rather than the sieve. I'm working in Euclidean. And in Euclidean, flux is quantized. So for beta, any one of these numbers, this is a shift by 2 pi I times an integer. And that's why the U1 global symmetry is broken to a discrete.
That is the topology of the challenge once you integrate over.
Correct. Sorry. So this is the statement that. Sorry, this is a slide to explain that the global symmetry is actually ZP, but these are details that we can skip. Then we use analytic continuation to solve it on this. And as I mentioned before, we're going to demand that our correlation functions only have coincident point singularities, which is picking a state for us. And that state is called the Bunch-Davies state.
Exactly, was it finally?
It's exact. You get it from a Fujikawa treatment of the path integral measure. I mean, you can compute it at one loop, but it's the full answer. Okay, so as I mentioned before, when we work on the S2, the path integral breaks up into flux sectors. They're also known as instanton sectors. And in each instanton sector, one important feature of this theory is that the fermions have 2k times p zero nodes in each instanton sector. So unless I insert instantons into my path integral and compute correlation functions, most of these instanton sectors do not contribute. For example, in the 0-point function, the k equals 0 term is the only thing that contributes. And yeah, sorry. One thing that we can determine from studying this theory is that can I write on the board? All right, I should have written this down in the slide. But if we pick a gauge, which is Lorentz gauge, so in my gauge, I'm going to write A mu is epsilon mu nu d nu phi. So this is chosen in a way such that the epsilon mu nu d nu beta from the chiral rotation, if I choose beta equals phi, then I cancel out the interaction between the photon and the fermion. So I'm going to label my photon this way, and And if I look at the action for that quantity phi, all of a sudden I see that I develop a pole away from zero in the action for the photon. So the photon develops a mass, and the mass depends on the coupling strength of the theory. So this was actually a very interesting realization. It was an important realization in the 1960s that you could start with a theory that has a gauge symmetry, and by strong coupling effects, the photon could develop a mass. This is the first place where you could show that the gauge theory doesn't protect the photon from developing mass. Gauge symmetry doesn't protect it. And that analysis holds true here too. Even if you put it on the sphere, that analysis remains valid. Now, in this model, we can compute anything that we want. One simple thing that we can compute is we can form a scalar from the field strength. We're in 2 dimensions. F mu nu has 2 indices. The epsilon tensor has 2 indices. So I can contract F mu nu with the epsilon tensor and form a scalar. We call that the electric field. It's F12 or 01 in Lorentzian signature. And we can compute the 2-point function of the electric field. In terms of that quantity phi that I wrote on the board, it's 4 derivatives of the 2-point function of phi. And that quantity you can compute to all loop order. And it's given by this function over here. You may recognize this function from the lesson yesterday. It's the free correlation function of a massive scalar. The mass is given by delta times delta minus 1. But now the mass is determined by the coupling strength of the theory. There's no mass parameter that I inserted into the action. It's just what you find. So the electric field behaves like a massive scalar, even though we started with an action that had no massive degrees of freedom. And you can take this answer and you can now compute its Taylor series around small coupling. And what do you find? So this would be the loop expansion of the theory. And at each order in the loop expansion, you find logs. So here's a log, here's log squared, here's a polylog. And you reproduce this theorem of Weinberg. You reproduce that at weak coupling, you get logs. And for a long time, people were speculating that these logs in de Sitter meant that something was going wrong. We only have access to perturbation theory, so we may conclude that the perturbative expansion doesn't work, so something must be wrong. But here's an example where we can sum up all the logs, and actually the resolution is very mild. There's no breakdown of de Sitter invariance, everything works out. So, if you ever heard people say that de Sitter is unstable, something like that, one of the arguments people use is along these lines, that there are logs that grow at late times. Well, that's just a statement that they haven't resummed all of the perturbation. So here we have an example. We can compute everything, and we can conclude that the logs resum. So actually, we've learned something. Very nice. And we can reproduce each one of these by a loop diagram in de Sitter. They're also nice. You can check the perturbative picture against this full answer.
But this is just for the Schwinger model, right?
This is just for the Schwinger model. Yeah. I'm not making a statement more generally. I'm just saying this is an example where we can see that it actually is okay. These logs actually do not signal a breakdown of anything. We can also compute the partition function and also compute its Taylor expansion. It's a very beautiful formula. Computing the 2-loop correction to this equation is extremely difficult. And I think a paper is going to come out soon by a former student at King's College, so keep an eye out for that. Yeah.
Contributions from these are they or are they going to make it stable or unstable?
Let's see. Let's see. So here, so far, the partition, like I mentioned, unless I put fermions inside the path integral, there will be no instantons that contribute because of the zero modes. So the bare path integral has no instanton contributions. So this is just no instantons. So now let's compute a fermion two-point function. That will have contributions from the instantons. So here's a fermion two-point function. And of course, the fermion is not gauge invariant. So we need to dress this with a Wilson line. And the Wilson line that we use to dress it is one that follows a great circle on the sphere. So it follows a geodesic on the sphere. And we can write down an answer. There's a contribution. So for the case of this analysis, I set p equals to 1. So p equals to 1. There is a contribution from 0 instantons, and there's a contribution from the plus or minus 1 instanton. And the 0 instanton contribution looks like this in terms of some functions g phi. I'm not going to give them to you because they're not very illuminating. The only thing that you need to know is that the 1 instanton contribution is down by a non-perturbative factor. It goes like 1 over the gauge coupling squared in the exponent. So if the gauge coupling is very small, this correction is extremely small, right? It's very suppressed. Typical instanton suppression. Now, what do we do? Well, now we have the full answer. Let's look at late times, right? We were interested in these late time correlators for the CMB. So what happens at late times? So let's analytically continue to Lorentzian signature. Let's use these coordinates. And let me look at the 0 instanton contribution. The 0 instanton contribution at late times, so I'm going to take this parameter eta going to 0. It looks like this. It's some number, x minus y over eta to the 1/2. And then in the exponent, you have x minus y over eta to the minus 2 delta with some coefficient here. Okay? And if I do the same late time limit for the plus and minus 1 instanton sectors, I find the exact same answer except a minus a here. And I think this was a shock to us, but the shock to us was that these two coefficients, a and a, are exactly the same. This guy is no longer down by instanton suppression. The e to the minus 1 over q squared that I wrote in the previous slide was erased by the late time limit. So the non-perturbative suppression and the late time limit don't commute with each other. If you want to have any reasonable control in this model of the late time limit, you need to know all the non-perturbative physics, which is very scary. I don't know what to make of that statement, but it makes me think that if this is a general lesson, it makes me think that we have no reason to trust a weakly coupled picture for inflation at all. And I don't want to make any strong statements, but if this is any lesson, then it's not a good one. So we still have some work to do. Okay, so I hope I've convinced you that this model is a good playground to learn things about de Sitter. Right? It's a model that you can exactly solve, and you can test a bunch of things that that people have said in the literature, but maybe haven't been able to compute before to such high accuracy. It's so an extremely fruitful model to study. I have about 30 minutes left, is that right? Okay, so right, so slide is just a summary of what I was saying before. We need to explore more models if we're going to learn anything truly or make any truly general statements. So what I would like to say is that what this model tells us is that we really don't know what's going on. And we should find other models before we proclaim anything, because we want to learn the general lessons, not just the lessons from one specific. Okay, so the next thing I want to discuss that this model lets us study is that there is some lore about de Sitter. And that lore is that any QFT with a global symmetry on de Sitter cannot have spontaneous symmetry breaking. So in flat space, you can have spontaneous symmetry breaking if you're at infinite volume. But there's a lore that says that you will never have spontaneous symmetry breaking in de Sitter. And I just want to remind you that for P equal to 2, 3, 4, our theory had a ZP global symmetry. So here is an example where we have a QFT with a global symmetry, and we can test whether or not that symmetry is spontaneously broken. Okay. Now, let me tell you why people say that you can't spontaneously break a symmetry. Well, the main argument is the statement that de Sitter is thermal. The ground state of de Sitter is thermal. And if you try to spontaneously break a symmetry, well, thermal fluctuations will restore that symmetry. Thermal fluctuations will restore the symmetry. You may try to break the symmetry by preparing some state, but if you wait long enough, the thermal fluctuations will explore the phase space, and you will restore this. Okay, so with a view to understanding the ZP symmetry in the Schwinger model, I'm going to first give you an example that I'm going to also put on de Sitter that has a ZP global symmetry. And I'm going to show you that that ZP global symmetry is spontaneously broken. But that model is, as you will see, is extremely trivial. Once I explain that model to you, we'll go back to the Schwinger model. Okay? Is that clear where we're going to go? And again, everything I'm going to say, we're going to use this picture of the relation between the sphere and Lorentzian. So we use the Euclidean picture, state preparation, and then we analytically continue to get Lorentzian business. So what is the model that also has a ZP symmetry that is also very trivial? Well, it's something known as the BF model. So have you guys seen this model before, the BF model, the BF theory? Yeah. If you haven't seen it, well, this is the action. It's very simple. It's a two-dimensional theory. Well, I'm going to give it in 2 dimensions. You can define it in any number of dimensions. But in 2 dimensions, it's particularly simple. It's a model of a compact scalar, which is called B, and the field strength for a gauge field. That's why B and F, BF theory. Okay. And when I say it's a compact scalar, I mean that B and B plus 2 pi are identified with each other. The zero mode is compact. The coefficient of the action of the BF model is the coupling of the model, and that coupling has to be an integer. Okay? So the players are B, F, and the coupling P. And F is related to the gauge field in the normal way. Okay, so this is the simplest example of a topological QFT. And this is why this is a trivial example. So the topological theory, I put it on the sphere. It doesn't really care that I put it on the sphere. Okay, so the field B and the gauge field A are canonically conjugate variables. And quantizing BF theory is very easy. And the one place where the fact that we're on the sphere comes into play is, again, that we have to work in flux sectors. So there is a parameter which is called K. These are the instantons. And we have to sum over all of these instanton sectors, just as before. So let's work in one instanton sector. How do we see that this theory has a ZP symmetry? Well, remember, B is identified with B plus 2 pi. However, if I shift B by 2 pi n over P for n from 0 to P minus 1, then the action only shifts by 2 pi I times an integer. Again, I haven't changed any of the physics. So this is an honest to goodness symmetry of the theory. And the reason that I don't go past P minus 1 is because if I take n equals P, then B goes to P plus 2 pi, and we know that B is a complex. There's only a discrete number of shifts for the field B, so this is a discrete symmetry. Okay?
You have taken B to be 2 pi over P symmetric from the beginning.
Can I say that again?
Could you have taken B to be 2 pi over P symmetric from the beginning?
Could I have taken B to be 2 pi over P symmetric? No, so B and B plus 2 pi are identified.
That's what you impose by hand.
That's what I imposed by hand. That one is a symmetry of the action. So you can imagine that the state has a potential that, so the theory, yeah.
You impose 2 pi periodicity because it's more interesting.
Right. Yeah, one I would call it a gauge symmetry, and the other I would call a symmetry, global symmetry. Okay, so this discrete shift is a symmetry transformation, and B is B plus 2 pi as redundancy. So this BF theory has this ZP symmetry. And what are the operators of the theory? Well, B and B plus 2 pi are identified, so B is not a good operator. Actually, the only good operator that I can build with B is the exponential of B. Exponential of B times an integer. The other good operator that I can define, which is gauge invariant, is the Wilson line. The Wilson line is e to the integral over a, some closed loop. And n also has to be an integer. The reason n has to be an integer is not so clear, but it has to do with the fact that the gauge group is compact. I would like to skip that argument if that's okay, but you just have to believe me that these operators are only well defined if these n's are integers as well. Okay? And you see that under the symmetry that I defined before, B goes to B plus 2 pi over P, these operators U are charged. So these operators are charged under the ZP symmetry. They're not neutral under the ZP symmetry. And in this theory, these operators are actually topological. Neither, they don't depend on X, and they don't actually depend on the loop around which you integrate. That's the statement that this theory is topological. You can insert this U anywhere. It really does not depend on it. But this U is charged under the symmetry. And the algebra of operators is very simple to write down. You conjugate U by the line, and you see that U just changes by a phase. And this phase is 2 pi I over P. It's a ZP phase. So this is saying that the lines actually measure the charge of this operator here.
Operator even is that extra factor that's what you mean after
that is charged.
Yeah, that's my question.
So think about like the Dirac fermion. Under a U1 rotation, the Dirac fermion changes. So that means that it's charged under a U1 rotation. But if I take psi bar psi and I rotate that one, then psi bar psi is neutral because it doesn't change under a rotation. That's what I mean by charged. That make sense?
Yeah.
This operator is charged because under a ZP shift, it changes by phase. And the charge is measured by the line. Now, notice one thing, this algebra over here is independent of if I shift m by p. If I take m goes to m plus p, then this phase goes to e to the 2 pi I m, and that's 1, so nothing changes. So actually, these operators need to be identified. There is a finite number of operators that I can write down in this theory. Um plus p and um are exactly the same. There's no difference. They have the same.
Since you are dealing with a topological theory, all your operators must be global operators. There are no local.
Correct. I'm writing it as local operators because it'll be useful for me later when I go to the Schwinger model. Okay, so this is a finite operator algebra. There's a finite number of U operators that I can write down. I might have thought that in the beginning I could write down U1, U2, U3, U4, U5, but I only have those operators up to UP minus 1. U sub p is equal to the identity. Okay, so now, how do I see that I can spontaneously break this ZP symmetry? Well, like I mentioned before, we'll just use the picture of Euclidean state preparation. There's a state 0, which is the Bunch-Davies state. I just do the path integral without any operator insertions, and I let this prepare an initial state for de Sitter. So now I'm going to imagine that I continue this into Lorentzian time. I have a Lorentzian de Sitter after this point, and this is going to be a de Sitter invariant state. However, I could have done the path integral, but inserted a U1 instead. This U1 also prepares for me a de Sitter invariant state. And I can do that up to p minus 1. And I can even show, using the Euclidean path integral, that these states are orthogonal. So this is an example where instead of having one de Sitter invariant state that I can prepare with the path integral, I have p of them. They're orthogonal. And so if I'm in any one of these states, the ZP symmetry is broken. Is that clear? This is an example where I put a theory on de Sitter space. It has a global symmetry. The global symmetry is spontaneously broken. Okay? And the thermal fluctuations on de Sitter don't perturb this. In particular, they don't perturb this because this theory is topological. It doesn't notice the temperature.
Say to this right? Usually say that obviously why the instance of this select configurations that are in the back or suppressed.
I have a good answer for you.
Okay.
But can I answer after the?
Yes.
Can I answer after the?
Yes.
I have a good answer, I promise. Yes.
Here these all of these are same energy.
Very good question. So this is a topological theory. In a topological theory, the Hamiltonian is 0. So all of them have the same energy. In de Sitter, remember, energy is not a good quantity. Energy is not conserved. So we don't really talk about energy generally in de Sitter, but in this theory, the Hamiltonian is exactly 0. All of these are degenerate states. They just differ by their ZP charge. Okay, so summary. We have a ZP theory in BF theory. It's spontaneously broken when I put that theory on DS2. So here's an example, albeit trivial, of a theory that I can put on de Sitter where I can spontaneously break global symmetry. Already we have gone away from the law. Right? The law doesn't work in this theory. We know why the law doesn't work. Theory is topological. Okay. So now you of course should complain that I'm trying to learn any lesson about de Sitter in this theory because the theory is topological. It's topological QFT. Topological QFTs don't really care about the background that they're put on. So the physics is independent of the metric. And if the physics is independent of the metric, physics is independent of the fact that I put it on de Sitter. So you should be yelling at me. You should say, how could you have tricked me in this way?
But is it immediate to think of the topology of de Sitter as the same as the topology of the sphere? And is it? I mean, the topology kind of does change if you go non-conformal.
Of course, of course.
So, but what is the argument linking that? I mean, we do it in flat space all the time as well. But...
Well, you're right. So yeah, the sphere is compact. The Lorentzian de Sitter is non-compact. So there are some subtle differences. But at the level of what I'm saying, none of that matters. The fact that the metric is time dependent doesn't really play a role in any of this. States thermal doesn't really play a role.
But I mean, the quantization condition we had from the sphere would.
Correct.
The foundation is right.
Okay, so how do I convince you that actually we can port these lessons to something that is actually reasonable for de Sitter? Sorry, I want to read this slide out loud. Maybe we can identify a QFT that in the IR is governed by the same physics, but in the UV is different, right? So in flat space, we might argue, well, if the IR is governed by the same physics, then we can, if we only care about long distance stuff, then maybe we can port these results and they would be useful. But remember, in de Sitter, the theory is time dependent. The Wilsonian paradigm doesn't work. We have to be very careful when we make any such claims. Okay, I really wanted to hammer that. You cannot use the argument that IR and UV decouple. So we can't really make the statement that if my theory has an IR phase governed by BF, then I can definitely conclude that this ZP symmetry would be broken. However, and yeah, this is the reason why. Remember, we can't decouple the UV from BF. So if I'm going to prove to you that there's spontaneous symmetry breaking in de Sitter, I need to have my UV theory, and I need to prove it to you in the UV theory. I cannot make any approximations along the way, otherwise you might complain. So let's do that. So let's go back to my good old Schringer model. Good old Schringer model, remember, because this quantity P over here was an integer, this model I explained to you had a ZP symmetry. And let's solve it another way than working in the original picture. There's a way to solve this model via Bosonization. The Bosonization transformation. In the Bosonization transformation, you take this current, the fermion bilinear current, the U1 current, and you write it down like this. You write it as the derivative of some scalar field times epsilon. This current is conserved. Current is conserved trivially because D of antisymmetric guy will just be trivially 0. And then we have this guy. This is the chiral current. And the chiral current, of course, is anomalous. And its conservation is the equation of motion for B, not necessarily 0. And of course, this B is going to be a compact scalar. So let's write down the Schringer model action. Schringer model action in the bosonized picture has a kinetic term for B, it has the Maxwell term, and it has this BF term. So in flat space, what we would say is the IR phase of this theory is governed by BF. The ZP symmetry is spontaneously broken. But now we can try to solve this model on de Sitter. And we can try to solve this model on de Sitter by constructing these states charged under ZP in the full model. So again, can't use the Wilsonian argument, so I need to use the full theory to show you that this ZP is. So yeah.
You mentioned that BF term is just a number, right? Once you integrate over space, it's just a number. That last term, right? D to X of that term.
It's just a number. No. So if there were no B here, that would be a number. That's the flux. But because B depends on space, it's not enough. Theory has a non-trivial operator algebra. It's the one that I showed you before. Okay, so what I need to do to convince you that this theory also shows spontaneous symmetry breaking of the ZP symmetry is I need to convince you that the full Schwinger model has operators like UM and WM with the same algebra as before, and that these operators are well defined in the full theory. Okay? They have to behave exactly as in BF theory. So one of them is charged under ZP symmetry. The line has to measure its charge, and I have to be able to insert it into the path integral and create states that are charged under the ZP. Okay, so in order to build these, I'm going to use two different currents. One is, I'm going to call it star J2. Maybe I should have changed the names of them for this talk, because using this notation isn't very useful. But this is how they're presented in the literature. So the only thing that you need to know is that this guy is a local operator, and this guy is a vector that has a vector in it. And you can see that if I delete this term and delete this term, this is the quantity that was exponentiated to give UM, and this is the quantity that was integrated to give WN, right? This is the local operator, this was the line operator, once I exponentiated it. And so now I'm just going to add a correction. The reason that I add these corrections is because these currents are conserved. They're conserved exactly. The equations of motion of this theory right here, this theory has equations of motion. I can write down the equations of motion of this theory, and if I write them down, then the equations of motion of this theory can be written as current conservation equations. D of star of each of these currents is conserved. So I can insert these currents, because these are conserved currents, I can insert them into an exponent and move them around. It doesn't matter where I insert these currents. These are also topological operators in the exact same way. The theory imposes these conservation equations as operator equations. So if I exponentiate these operators, then they're also topological operators, just like the U and W operators in BF. I can verify that these current conservation equations just follow from the equation of motion of the theory. And then, if I want to build the operators that I had before, all I have to do is exponentiate J2 or exponentiate the integral of J1, and these operators have the exact same properties as in BF. Okay. And they also admit the same algebra as in BF. So then I can go and compute the same exact thing using the full path integral. I have the ability to compute the full path integral for the Schwinger model. I just insert these operators now in the path integral and produce these states, and I can check that just as before, I have P states that I can produce this way. They're all orthogonal, they're all de Sitter invariant, and they're all they all have the same energy, although energy is not the right term. They're all equivalently de Sitter invariant. That's the important thing. So here we have a UV model. I didn't have to make any approximations, where we can conclude that, again, the ZP symmetry is spontaneously broken. And this model is not topological. It cares that we put it on de Sitter. It can feel the de Sitter temperature. So here's an example where if you try hard enough, you can again show that that global symmetries can be spontaneously broken, even though the physics of de Sitter is. Okay, so I skipped one caveat, and this is what I'm going to end on. is that actually the one difference with the BF theory is that when I exponentiate these local operators, I have to regulate this theory. This theory I need to define a regulator in order to make sense of these operators. And I haven't told you how I've done that. So I'm not going to tell you how I do that. You're going to have to wait for the paper. But I just want you to trust me that this is doable. That's all I want to say. But modulo that statement, we can show that this physics is robust, that this symmetry is spontaneously broken in the set. And if we compute correlation functions in these various states, they behave, if they're insensitive to the charge, the ZP charge of the state, then they behave exactly as if you had prepared just a regular Bunch-Davies state with no insertions. Very difficult to tell that you're in any one of these different states. So we could be in some spontaneously broken state and never know it by performing local experiments. This is a very interesting. Okay, so in conclusion, we can learn a lot by studying examples. Thank you.
All questions for our speaker?
Maybe can I ask another version of the previous question? Maybe you ask again. So there is also the law that in quantum mechanics we Engelbrecht contained this infinity, right? Like we have double well, the actual part in itself. But then there are some cases in which you can evade this, like if you because you have the terms or there is some and in that case, these special models, like there's some cancellation between the tunneling doesn't happen, right? So does this feel in the same? If it is the same feeling here, it's something that suppresses the tunneling, or
Yes.
in a sense, I'm asking, do you expect this to be a generic feature or a feature of special theories that suppress tunneling?
It's a feature of special theories where the tunneling is suppressed.
Okay.
So now maybe I can answer your question, the previous question. So I didn't say this, and the reason I didn't say this was to save time. But this theory has two global symmetries, not one. As the ZP global symmetry, which is called the ZP zero form symmetry. This theory also has a one form symmetry, and the truly robust statement that people make is that the ZP one form symmetry is spontaneously broken. People prefer to work with spontaneous breaking of the one form symmetry rather than the zero form symmetry. The reason why is that I start with a state which has zero form charge. I can act with local operators and change the zero form charge, right? So it's easy to go from one zero form state to another, and maybe you might restore the symmetry by acting with local operators. However, the entire construction that I told you here can be done with the one form states. And now the only way to change the charge of the one form state is by acting on all of space with a line operator. So it's impossible for a local observer to change the charge one function. And this is the thing that makes the spontaneous symmetry breaking robust. You have to act on all of space in order to tunnel, and there's a huge suppression of that. It's just impossible.
Do you expect some of the aspects you discussed to be strongly dimension dependent? Because I mean, you're in 2 dimensions mostly, and okay, some things that work nicer usually.
So this example, solvable models, I don't know of any in of course, that doesn't mean that they don't exist, but I don't know any, and I would like to find some. However, for this spontaneous breaking, I can run a version of this argument in 4 dimensions. There's a theory that I can put on de Sitter, and it would work the same.
Maybe not the most relevant question, but what happens if you consider gravitational back reaction? So
that's you mean for the perspective of this symmetry breaking? I think that you would restore the symmetry. Global symmetries are restored when you fluctuate the background. But they would be restored by non-perturbative effects, which are like wormholes or Euclidean wormholes. You need to consider higher topologies. There's going to be a version of that argument that appears in the paper once it finally appears.
Okay.
All right. My hope is within the next few weeks, but you know, that's not how life works.
Okay, if there are no more questions, let's thank our speaker again.
Right. Perfect.
All right, so last but certainly not least is sale, and so talking was about some very complexity in our system.
Thanks, Gary. And I just want to start by thanking the organizers for this workshop. It's really been fantastic. And I also want to thank Anosh for the concession to push my talk to the last day. The paper that I'm going to base this talk on actually appeared this morning. So we made good use of that concession at the end. So the work I'm going to discuss is on tensor product systems, spread complexity, with Jeff Murgan, who's also in the audience. And so spread complexity is a concept that many may have heard, not necessarily know all the details. I'm going to be pretty scant on motivation for why I'm considering it. There will be one slide after the discussion on spread complexity. But what I'm just going to do is I'm going to define what the quantity is, and then give you some pretty general results, surprisingly general results to me at least, when you consider tensor product systems. All right, so there we go. So just as a brief background on what spread complexity, where it fits into this basic idea of complexity. And the idea is that in complexity, you want to ask how hard it is to synthesize a desired target state with some set of gates at your disposal. So what's in the game is a reference state, typically a simple state, some target state that you want to construct. You have some set of unitary operations at your disposal, and then also a metric, a way to quantify, given that sequence of unitaries that you've used, some number. That tells me how hard was this to put together. So as a very simple cartoon example, think of a system with 3 unitaries, you've got a reference state, and there's some targets that you can construct with some sequence of unitaries. You may run into a situation where a particular target state can be generated in many ways, in which case you'll have to decide, well, what's the total computational cost on the left and the right hand side, and the one that gives you the lowest cost is the complexity. The complexity tells me what's the smallest computational cost given the operations and reference state at your disposal, how to generate the defined target state. Now, what I've sketched here is a discrete notion of complexity. You can imagine this being very relevant in quantum computational setups, where you have some quantum state that you want to generate. You have some set of quantum gates that you can put into your circuit, and complexity will be the most optimal circuit, the cost of the most optimal circuit to get you to the target state. There's also continuous notions of symmetry, introduced by Nielsen famously, that's And there's some really nice connections between spread complexity and filter complexity, but I won't have time to go into those today. Our main focus is just going to be on this concept of spread complexity. On UI MBA. One of the main criticisms of Nielsen complexity is that it's extremely gate dependent. What is the set of unitary operations that you have at your disposal? So the authors in this 2018 paper tried to introduce an idea that's less redundant. And they said that, well, if you give me a particular quantum system, then one natural operator that appears is the system Hamiltonian. So let's take the system Hamiltonian as one of our operations. We can manipulate states acting with the Hamiltonian any number of powers on a reference state. So this gives me some basis. This basis is not necessarily orthogonal with respect to the Hilbert space in the product. So there's a second operation, and that's the ability to take superpositions. Taking superpositions and actions of the Hamiltonian, you can build an orthogonal basis sequentially. So start with your reference state, that's K0, act of the Hamiltonian once, orthogonalize what you get, then you get K1 and so on. And this gives you this orthogonal basis, the Krylov basis, and now I'm just going to invoke this cost function that the Krylov complexity is given by sum over the Krylov basis, project your target state onto the Krylov basis, and assign to the Kn basis weight n. And the way to think about that is that K0 has a cost of 0, K1 has a cost of 1, K2 has a cost of 2, and so on. So it's an ordered basis of complexity. This choice of n is not strictly necessary, but it's the most commonly used one. Fine. And it's an ordered basis for the space of target states that you can construct. Just one point to note, this will be a little bit relevant perhaps later. The dimension of the Krylov subspace, if you give me, it's usually written down as dk, and if your reference state is a superposition of n eigenstates of the Hamiltonian, then the dimension of the Krylov space is at most n. But there could be additional symmetries in the state that you're considering, which will make it less than n. It's usually due to symmetries that there's a reduction in the number of Krylov basis vectors that you construct. Now, you may have one criticism. I said that this was first introduced as a way to pull complexity in a more redundant-free way, or not redundant-free, but fewer redundancies. But this cost function we've written down is certainly dependent on the basis. So why the Krylov basis? There's a naturalness argument for why the Krylov basis is the appropriate one to use. It's basically the following. If you were to consider any other basis, and you compute and you say this basis, I'm going to build a similar cost function, increasing numbers, and I compute the complexity of the time involved the reference state. Then the choice that minimizes that cost function is the Krylov basis. So the Krylov basis is a natural choice to use. There's a second perspective that you can also take, and that is that what Krylov basis really is complexity with an appropriate choice of cost function given Hamiltonian and superposition. And this also fixes the Krylov basis as the minimum choice, the best choice that you can put together your basis. But with that out of the way, just a short slide on where this fits in, why this is relevant. Well, in quantum many-body physics, it's been proposed as a probe of all sorts of interesting properties of physical systems. So chaotic dynamics, for example, there's claims that spread complexity can be used to probe whether a system is chaotic or not. But there's transitions from integrability to chaos, topological and PT symmetric phase transitions, and also recent work that might be relevant in the quantum N-by effect. Also in holography, for these complexity equals action kind of conjectures, it's also found there. I'm not going to spend a lot of time on this. I'm interested in asking far more basic questions about this mathematical quantity and what happens with it. So before I get into that, let me just maybe present the most popular way that the Krylov basis is generated. I think this will give some insight into why the results are what they are once I get to tensor products. So the way that you would generate the Krylov basis, one has to be first. So I already have my reference state. I'm going to call that K0, the zero complexity Krylov basis vector. I can generate the first Krylov basis vector by acting with the Hamiltonian once and taking an appropriate superposition of that with K0. this generates K1 for me. I've basically just subtracted off the projection of that state onto the zero Kirov basis vector. Another way to think about it is I active the Hamiltonian once. I'm going to generate things that I've seen before, proportional to K0, and some new things. I isolate the new things with an appropriate superposition. I can active the Hamiltonian again. And now I'm again going to generate things that I've seen before, proportional to K0 and K1, and some new things. And I'm going to call those new things K2, after appropriately normalized. And so on. Do this in a recursive way and you generate the full Kirov basis. And one interesting thing to note, though, is that if you consider an emission Hamiltonian, then actually, when you active the Hamiltonian again, I'm not going to generate anything proportional to K0. Hamiltonian, if it's emission, will be tridiagonal, the Kirov basis. So what's happening here is that you're taking an arbitrary Hamiltonian and reference state, and you map the dynamics of this onto this Kirov chain. So it's a nearest neighbor chain. Each point in the chain is a Kirov basis vector, and there are these hopping coefficients, or branches coefficients. Stated in an operator way, you've given me a generic Hamiltonian, and I've decomposed it into three operators. One that's pushing me forward along the Kirov basis, along the Kirov chain. One part, it's emission conjugate, that's hopping me back, and one that keeps me at the same site.
So these Ks, their states are operator?
Sorry,
They're both.
I couldn't get.
No, I'm asking whether this Ks, they're operator or states.
States. And this case, I'll be focusing on states specifically. There's also a formulation for operators. This is really what's meant by Kirov complexity. But I'm primarily focused on states.
How do you choose K0? Is there some, it has to be generic enough, right? If K0 is
So if you want any robust features of a Hamiltonian to show up, you need to show that it's sort of robust under different choices of K0. But yeah, you'll make some choice for K0. The Kirov basis will depend on that choice. It will depend on your reference state as well as your Hamiltonian. In the context where I'm going to work, at least in the examples, these will be simple Hamiltonians from some symmetry algebra. And there's some nice ways to manipulate the reference state by just acting with the elements to move it around different points in the manifold, different appearance states. So in that way, you can get reasonably robust.
And so in your last point, you say in general that the page is not the machine. Is that right? Or
So this, I believe this is general eigenvectors. I will be focusing on the case of an emission Hamiltonian, but in general, the point is that you generate the Lanchus or the Kirov basis recursion. So in general, you will have a part that will push you forward along the Kirov chain. Right? It might not be a nearest neighbor Hamiltonian if it's not emission, but you'll still have these two. So just before I dig into the tensor products, I'm just going to try to be quick. Why am I interested in tensor products? It's essentially because what you would like to do with any sort of mathematical quantity is find cases where it simplifies dramatically. So there are known cases where you get analytic results, and that's for rank 1 algebras. The Hamiltonian is an element of issue 2 or issue 1, or the Heisenberg algebra, and you get analytic results for any choice of reference. So you can write down exactly what the complexity is, but beyond that, people need to resort to numerics. There are no sort of nice expressions that you get if you look at other models, though certainly for finite dimensional ones, you could write those down. And just maybe give you some insight into why this is possible. It's because the Kirov basis is known explicitly, starting from the lowest weight state. You start from the lowest weight state, you active the Hamiltonian recursively, you'll just start laddering up in this multiplet, and this will generate the Kirov basis for you. So that's known in closed form. And this is why these results are known analytically. And as I mentioned, you can change the reference state with some group operation. So in this way, you can obtain the results for any two state. But what you'd like to do is look at the next simplest case, and you'd expect that to be tensor products. Can you make some progress in understanding what happens in tensor products of these items? So what I have in mind specifically is I have two subsystems, H1 and H2, and I'm going to assume that I know how to build the Kirov basis for both of these. And now I'm just going to consider the combined Hamiltonian and consider what happens with the Kirov basis and the spread. Now I'm going to start off with an example. This is sort of the simplest example that you can write.
Sorry, by H1, you means H1 and tensor product of identity?
Absolutely, yeah. So I'm not very careful with that notation, primarily because of space constraints. Otherwise, the equations get a little bit small, but certainly, yes. You would have to tensor, I mean, have H1 tensor identity plus identity tensor H2, absolutely. And the complexity you can compute for any target state, but a very natural choice is often the time evolved reference state and how this behaves. And I'm going to usually call that CT. So there are three quantities in the game. That's C1 of t, where I take the reference state phi1, evolve it with the Hamiltonian H1 to generate Kirchhoff basis. I do the same with H2 and the second reference state. And then for the third one, I'm going to take this tensor product Hamiltonian and act on the tensor product reference state. I'm going to compare what you get for different values of alpha. What you immediately find is something like this. So here is the result for the sum of the two complexities in yellow and the complexity in blue. So this is one plot that you can generate. Second plot would be change the values of alpha. This is what you generate. You work for a lot of these examples, and what you'll notice is that the combined complexity, C12 for the tensor product system, always appears to be larger than the complexity of the sum of the two subsystems, or the time evolved reference. I've just shown it here for two very simple examples, but we work for a lot of examples, and you see this all the time. And you come to think that this must be a general property. So is it always true, and why is it always true? That's something that we would like to understand. What I'm going to show you is that it is actually always true. I'm going to try to give you some insight into why that is the case. It's actually a really simple reason. So it turns out that even though this seems like the more simple question to ask, that I have this complexity of the time evolved reference state, and this always appears bigger, it's actually better to ask the more general question. I have a complexity operator for the combined system, and I'm subtract off the complexity. This is some operator. Again, I've omitted some tensor product of the identity, and that identity you can resolve in terms of Kirchhoff basis as well. I've just dropped them for space considerations, but this is some operator. When I take the expectation value of the time evolved reference state with respect to this, I'll recover exactly that quantity there, C12 minus C1 minus C2. Well, I can do this actually for any state. And the reason it turns out to be better to ask it for all states is because actually this operator delta is semi-positive, which you can prove. So not only is this statement true for the time evolved reference state, it turns out to be true for every state. Every state supported on the Kirchhoff basis, you will find positive. When I first saw this, I was quite surprised by that. But after retrospect, it's actually quite obvious. If you think about this in a computational way, the subsystems, I build them with two operations and superpositions. The Hamiltonian for the one subsystem and the Hamiltonian for the second system and superpositions. But when I put together this tensor product system, I have superpositions and just a combination H1 plus H2. So I don't have in particular the combination H1 minus H2. So I have fewer operations with which to generate the target state. So I should expect that to always be more complex, more computationally expensive. You can be lucky that they are equal, but beyond that, they will be. Let me do that in a bit more detail. So that was very qualitative. Let me show how this comes about, how we can prove it. There's a single simple observation that allows you to prove this. It's the following, that if I act with a Hamiltonian n times on the reference state, I'll get a superposition of first n Kirchhoff basis vectors. This is just due to the recursive nature of the algorithm. I don't generate any Kirchhoff basis vector with an index greater than n. So if I consider the tensor product Hamiltonian, well, this is going to be H1 plus H2 to a power of n. The right-hand side will, of course, have some binomial expansion, H1 and H2 commute. So this is the simple expression that you get. And what you notice is that the sum of the two indices, I should mention that H1 is going to generate some superposition of the K1 Kirchhoff basis vectors up to n minus k, and H2 to the k is going to generate Kirchhoff basis vectors up to K2k. What is that if you recombine everything into the sum of the indices of K1 and K2, then the state here with the sum of the indices being N, and then the relative differences being anything, this only starts appearing at the N. So, everything that I could generate with N combined applications of H1 and H2, that will only start appearing. Very simple observation, but this is all you need to prove it. So because of this, this implies that these states NA, so these are just the usual tensor product states, so the natural basis to use for the tensor product vector space. When I expand that in terms of the Krylov basis for the combined system, I will start at Q is equal to N and everything beyond. And using that, you can now prove that an operator is positive definite. You can do it iteratively by actually building up every possible state in the Hilbert space until you get a positive overlap. I'm just going to give you 2 examples from that general proof, but you can see the general proof in the paper. So the first is the simplest case, just consider diagonal elements. So in A, so these are eigenstates of C1, C2. They sum to N in the indices. This I get from the expansion in terms of the Krylov basis. So the Krylov basis are the eigenfunctions of the combined Hamiltonian, and I get a sum from N up to big N, the Krylov space dimension for the combined system, and these coefficients. And you can reorganize that sum to be a sum of positive differences. Essentially, all the differences from K is equal to 1, so everything that's larger than, or Q larger than some positive terms. So this is positive. But of course, you need the off-diagonal elements. So let me show you one example with the off-diagonals. I'm going to just take the superposition of 2 states. Again, the more general proof is the paper. But if you have this superposition of states, I'm going to assume P greater than N without loss of generality. And we just need to start collecting the terms. This off-diagonal element can expand, and you eventually find out that this is how the sum reduces. So again, get the sum of these complex terms plus Q times that sum. That sum on the right-hand side vanishes due to orthogonality of the states. So that vanishes. I'm just left with this one over here. And everything starting from P, which is the larger of these 2 numbers, start contributing, all these coefficients. And now when I collect them all together, the diagonal elements for P, that's that sum of, this sum of positive terms. Here I already have the off-diagonal term. And then the other diagonal term, I can actually drop a bunch of positive terms. Just be left with this. These I can combine into what I think that's again just the sum of positive terms. So, and yeah, you can keep going, construct every state in the Hilbert space, in the Krylov subspace, I should say, to show that this is a positive different one. So this is quite interesting. It's not just true for the time of alteration state. It's true for every state on the Krylov subspace. So we've shown it here for tensor product of 2 systems, but by iteration it also holds for the tensor product of many systems. Because I can take, for example, the free system case. First, just take a tensor product of 2 of them. That gives me the Krylov basis for the combined 1 and 2 system. Then take its tensor product of the third system, and it must be clearly. So this is a general fact that you can write down. What about the dimension of the combined Krylov subspace? Well, if the dimension of the 2 subsystems are N1 and N2, I should say it's N1 plus 1 and N2 plus 1. I've used N here to denote the largest index that you will get. The index runs from 0 up to N1, 0 up to N2. But they satisfy these inequalities. This just comes from the the fact that the Lang's algorithm will terminate for the 2 subsystems at this, at N1 and N2 respectively. So you must have at least that many states in the combined system. And the right-hand bound simply comes from how many states do you have in product Krylov spaces. So the lower bound is saturated. This is something that we also prove if the 2 subsystems evolve synchronously. What I mean by synchronously is that the ladder operator that you get from decomposing the Hamiltonian for the Lang's algorithm is just the sum of the ladder operators of the 2 subsystems. So the way that you push forward in the combined Krylov chain is just the sum of the two planar operators. And this, if this is satisfied, then you have a total of N1 plus N2 plus 1 states in the combined Krylov system, and that satisfies about the inequality. Now this operator that I defined before, delta, that's the difference of the two complexities. This is a semi-positive definite operator. So this quantifies excess complexity, additional complexity due to the fact that you only have the tensor product Hamiltonian H1, H2 at your disposal. What you can show is that the first two Krylov basis vectors are unaffected, and then depending on the Hamiltonian, the second Krylov basis vector might be affected. So this is a later time effect to the form. Right, so for the example that I showed, alpha 1 and alpha 2, this, let's just go back to an example. This idea of synchronicity, this occurs when alpha 1 is equal to alpha 2, or alpha 1 is equal to minus.
So in your model, H1 and H2 is completely disjoint, right? There is no actual interaction between, so it's more like a mathematical formalism kind of thing. And more like a mathematics around trial of complexity. There is no interaction between one.
No interaction. So yeah, I'm just interested in the most basic kind of setup. So the hope is that you would get some analytic handle on this case. But we are certainly interested in extending the picture that we get here to those cases. Absolutely. Right, so you get synchronicity if those two are satisfied, and it's because there's an additional symmetry that shows up. An additional symmetry is that the Hamiltonian commutes either with the Casimir that you get from the sum of the chains, J1 plus J2, plus minus and J and zeros, or the ones that you get from the minus. So the Hamiltonian commutes with that. My reference state is the lowest weight state, also commutes with them. So I can only generate Krylov basis vectors that have that same, that have that symmetry. Oh, there should be an N over here that I missed. This is a family of states that you write down in analogy with at the synchronous limit. That would be the Krylov basis. But what if I'm slightly away from the synchronous limit? That turns out to be an excellent approximation for what the Krylov basis vectors are. There's just a small deviation from it. And you can see that in the plot. So that at early time, at the close to the synchronous limit, the excess complexity is really tiny. But of course, it says nothing about later times. You can still get excess complexity that goes up to the Krylov essentially. Yeah, I have J1 and J2 is equal to 2, so 60, etc. I won't have time to go into the description of the Krylov graphs, but this is a nice way to visualize what's happening. So you have two terms in the Hamiltonian of the combined system, one that's pushing you along layers of equal n plus n, and another term that fuses you on each layer. And the continuum limit, you could really think of this as a drift and diffusion kind of equation. So you have these two components, and I should add that the diffusion part of these dynamics only shows up once you take a tensor product of at least two systems. In a one-dimensional case, you just have a drift. But you can really visualize it nicely in that way. So just to conclude, we've shown in the general proof that spread complexity is super additive on the tensor products. And it's additive if and only if the two systems evolve in synchrony. So no diffusive spread within the subspace. You will generate exactly one eigenstate to C1 plus C2 using your action of combined Hamiltonian. And natural equivalence advice we'd like to explore further. What's the physical information that's contained in excess complexity? Are there implications for spread complexity as diagnostic for example, quantum chaos? And then can we consider algebras that aren't just the sum of computing terms, but have much more connected structure and something like issue 4. Hopefully, some of the tools we've developed here can be useful. Thank you for your attention.
Questions, Stephen?
So as I was saying that these systems are free, so I would expect naively that an ideal measure of complexity would just be complexity of 1 plus 2 is equal to
Absolutely.
complexity of 1 plus, yeah.
I should have mentioned this follow-up. So if you consider something like Wilson complexity, that's absolutely the case. But what you've done when you've taken the tensor product and Wilson complexity, you've also enlarged the set of gates that you have at your disposal. I have all the gates manipulating the one subsystem and all the gates manipulating the second subsystem. I've put them together. Here, this tensor product, you've only taken a tensor product of the states, but you don't have all possible linear combinations of those operations at your disposal. That's why you get this super additivity here. You can consider generalizations of Krylov complexity where you also enlarge the set of operations. In that case, I think your intuition is correct. You will certainly get that they are just additive. But that's an important question. I've seen a few places in the literature that assumption. I just think that it's just going to be the sum of the two, but that's general model.
Set of operations.
So in this case, it would be H1, you have H1 plus H2, but also H1 minus H2. So the linear combination. Those are your two allowed operations. And then you have
I mean, almost, yeah.
and superpositions.
I don't know much about this, but it's kind of really just recently. So you must be similar.
Definitely, yeah. So in fact, here I've not assumed even that the operator I'm using is emission. It's just a consequence of the way that the Krylov basis is generated. It's really underpinning all of it. So you could use any operator. And a nice generalization would be a concept of multi-C Krylov complexity. What they have there is they still have a system Hamiltonian, but they have a family of states that they define as zero complexity. And these are typically related by some operation. And so in that way, you have, more operations than just Hamilton.
And a related question. So as you're talking about multiple systems, is there an analog of that results for multiple systems? Like if you have